Hey guys, this is lecture 1. What is a vector? I've got a joke for you. What do you get when you cross a mosquito with a mountain climber? Nothing. You can't cross a vector with a scalar. It's a pretty terrible math joke. And until you cover the mathematics of vectors and specialist math or math methods through year 11 and 12, you're not going to quite get it, but you will down the track. So this video will be covering the main ideas of chapter 10.1 of your textbook, and you should complete the reading of that before this class. Now, here are the learning intentions and success criteria for this chapter. I'd like you to pause the video and I'd like you to complete the knowledge and skills table. So using these headings, please record right down there and right underneath it what you think is the knowledge from looking over this and what you think is the success. Alright, now hopefully in looking through that you identified the following things. That for knowledge you should be identifying what is a vector, and you should be identifying what are some quantities that are and aren't vectors. We knew that from the fact that we've got a define here and this categorize. These are both knowledge type verbs going on here. Underneath skills, we've got these last two here, represent and recognize, and we see, can you represent vectors in different ways? And finally, can you recognize vectors when they're written, because they will be written to you in your textbook and they'll be written to you in your final exam at the end of year 12. Okay, let's get into it. So, I have a question for you. If we stand next to each other, and I walk, and you've got your eyes closed, and I walk 5 meters directly away from you in a straight line, and remember, in class I'm very sneaky, you generally don't hear my footsteps, where could I be? Let's look at this visually. So, firstly, here's us. Here's you, and here's me. Now, here is a path that I could take. And we said that was 5 meters. Here's another path I could take. Hopefully they're pretty close to the same length. And I can draw a few more of those if I want to. Now, I'd like you to pause the video. I'd like you to take that as well, and I'd like you to draw a few more lines. And what I want you to try to look at is, what is the shape made by the end of the paths, where the line ends up to. Okay, now hopefully you've had a go at that, and if you have had a go, hopefully you would have seen the following, that it basically comes out as being a circle. So I'll draw a few more lines here, and they're all reasonably close, but if I connect the ends of each of these, we can see that with my terrible drawing aside, we roughly have a circle. So what was missing in my original question in order for you to know precisely where I am? Okay, not where could I be, but where am I definitely? And the answer is direction. Right. Now, if instead of saying I walked 5 meters away, I told you that I walked 5 meters east, and you actually know what direction east is, you'd be able to predict where I was a lot easier. So if I draw on here, 5 meters east, the only place I could be would be right here where that red dot is. Okay. So, this leads into our definition of what a vector actually is. So, a vector is a physical quantity that requires both magnitude and direction to fully describe it. Now, this is a definition that you should write down. You can also check the glossary of your textbook as well as the syllabus to help reflect on these as well. But the word magnitude here is just another fancy word to mean size, how large something is. And direction in this case could be as simple as up or east, or something a bit more complicated as 30 degrees true, or perhaps something like south 16 degrees west. These are all things that you would have seen in Year 10 mathematics, and if you did any classes with me in Year 10 you may have seen it as well. Okay, so is there anything that we've done in science class over any of your years, go and try to throw your mind back to grade 8, where we've measured something that didn't actually need a direction. There's some things that you may have clued in that we need directions, things like direction. Direction can use directions. Distances can use directions, I should say. So what else have we looked at that doesn't need a direction? Now these are a lot more common in science. Things like mass, time, temperature, energy. None of these have directions, and these are called scalars. Now this is our definition for a scalar. A scalar is a physical quantity or measurement that only requires a magnitude, remember magnitude means size, to describe it. So as I said before, mass and time, these are both examples of a scalar, because we don't say 10 kilograms of potatoes northwest. We just say that the potatoes have a mass of 10 kilograms. We don't say that it took 2 hours east for the movie. We just say that the movie is 2 hours long. But when we look at direction, we see that when we look at distance, we see the direction actually matters a bit. If I tell you travel 5 kilometers, well, there's a lot of places you can go in 5 kilometers. If I say travel 5 kilometers due east, there's only one place you can go. Now, I'd like you to look at Table 1 on page 274 of your textbook to see a comparison of vectors and scalars. Some of those should be somewhat familiar from our classes over the previous years. A couple won't be, and we'll see them as we go through the course over the next 2 years. All right. Now, the first thing we really need to understand for a course of physics here, especially when we're dealing with motion, is how to represent direction and how to represent coordinates. When we talk about displacement in the real world, we'll use things like 3 kilometers east, or Johnny traveled 2 meters up, or Lena went 5 meters southwest. But using directions is very hard to do mathematically, and so some conventions do exist. When we say that somebody travels east, or sometimes we might say forwards instead, okay, we give that direction displacement a positive value. So if 3 kilometers east would just be written as plus 3 kilometers, and because mathematicians are lazy, we generally don't write the plus. If Johnny here moves west or backwards, we would give that the negative direction. So 5 kilometers west would be the same as writing minus 5 kilometers. And the minus in this case has to be there. You can't skip that through laziness. If this is in what we would call the horizontal plane, if we're talking about the vertical plane, when things move up and down, if little Johnny here is moving upwards, again, we give that the positive. So if we were saying that he's moving 2 meters up, we would just say that that is plus 2 meters. If, however, little Johnny here is moving down, we give that the negative value. And so if we had, say, he was going 4 meters down, mathematically we will write that as minus 4 meters. In that case, remember the minus is important. And now, these are the general ones I use, and it's a general one that the author of the text uses, and it's sort of the basic convention. You can change it if you want to. You've just got to make sure that you communicate your conventions. And even using the ones that are pretty standard, you still need to communicate them when you are writing or when you're doing working out in exams. Now, there's also the issue of what does a zero mean? Okay, now the text has some really good images showing this, so make sure you check the textbook. It's around 274, 275, and they show what the zero would look like for both horizontal and vertical systems. And you can place 0 at the start, but sometimes you can place it in different places to just help with the math. So you should try to be flexible with it. Sometimes you might put 0 at your destination because things are falling towards a spot, starting from a height, or you might put them at the 0 at the very beginning, or you might put the 0 level with an object that you're passing. So 0 can have a couple of different places, and you'll see some examples of this as we go through. Okay. Now, vectors can be represented in a couple of different ways. Now, we've seen over previous years that different physical quantities have a letter. Some that you probably have seen, capital T for temperature, where temperature is, in this case, measured in degrees Celsius or Kelvin. M, lowercase m, for mass. And just to be confusing, because there's lots of things in the world, lowercase t for time, in seconds. It is really important to make sure that you do use the correct upper versus lowercase. You cannot be lazy with that. Okay, be very, very careful. But vectors, there are things that are vectors, like velocity is one that you would have seen in year 10, also has letters. But outside of knowing that velocity is a vector, there's no way to tell by looking at this v that this is a vector compared to these. Okay? And while you should know that velocity is a vector, or hopefully you can remember velocity is a vector from last year, when you're looking at other things in physics that you may have only just been introduced to, or you may see it for the first time in a text, you need to be able to see communicated to you that they are vectors and recognize that the text is telling you that it's a vector. So we give the vector symbols like velocity a little bit of symbols. They can be bold, so this one's a little bit harder to do with handwriting, but just a slightly bolded V. That's a pretty easy one to do on a computer though, so if you want a simple one to do on a computer, bolding the vector is perfectly fine. You can give it a hat, so V with a little hat. You can give it an arrow, so V with a little arrow over the top, and it might be an arrow with the whole arrowhead around it, or it might be an arrow with just half of one. Some texts will use this version instead. Finally, it can actually just be drawn as an arrow. And the length of the arrow and the direction the arrow is facing tells us stuff about the vectors. So these are the ones that you would expect to see in exams or expect to see in textbooks when they're talking about things. This one is useful when we are doing some mathematics. Now, you can choose whichever one you prefer when you're doing your own text or your own assignments. I'm partial to the hat. It doesn't matter what you do, what you like, but you do need to be able to recognise all three for your Year 12 exam. Now, take a look at the examples on page 276, please, because they will show you how different vectors are drawn. And I want you to take note of the angle between the vector and one of the main directions, whether north, east, south, or west. Some texts do get pedantic and say you should always choose the small angle. Note that example B there has a 70 degrees from west when there is a 20 degrees from the north right next to it as well. So if I have coordinate system and this is 70 degrees from west, so it'll be up that way. Well, this is a right angle between north and west because it's 90 degrees around, so if it's 70 there, it'll also be 20 there. Some books say, oh, you should always do the smallest. It doesn't matter, okay? I'm not going to penalise you for it. There's no requirement for it in the text. If I was asking you to give me the angle for this, it wouldn't matter which one you gave. Okay, now you won't have to work with these picture forms of vectors that you can see on 276 there very much. There are some problems down the track. It solves a bit faster, but you're not going to get bonus marks for pretty math, so don't stress. There is a simple, straightforward way to always do vectors that always works. However, you may find that it's just a matter of working your way through these things. Okay, that's the end of our first lesson, so let's have a quick summary. So in this video you've learnt the following: how firstly, what vectors and scalars are, and we've got some examples for them. We've learned how to represent directions as either positive or negative numbers by convention. And then finally, how to represent vectors in different written forms or using arrows. Now, when you come to class, I expect you to have completed the entrance slip. For your entrance slip, you will need to access your O book and download the Chapter 10.1 Check Your Learning PDF. You can use the printed text and just look at the questions in the text. However, if you wish to just put your answers into the PDF, it might save you a bit of paperwork and stuff like that. And I want you to complete questions 1 to 4, and I want you to copy those answers for 1 to 4 into the 1.1 space on eLearn. It is right underneath the video link that you followed to get to this video. Thanks guys, see you in class and see you in the next video.